with lecture. Yeah? So this week we start with a new topic. So let me just share my screen. Okay. Okay. Just to orient ourselves, this is week 3. Yeah. So as you can see on the screen, right? So week 3, we're going to look at the next chapter, which is chapter 4, STP, or Spanning Tree Protocol, right? And just looking ahead, next week we'll be covering 2 chapters. First one is Ether channel and then FHRP, right? So we do this STP first because when we discuss Ether channel, right? So our discussion on the chapter 5 refers back to STP, right? So that's why we're going to look at STP first, and then when we look at Ether channel, mentioning STP should be clear already lah. What's STP, right? Okay, so now that we orient ourselves already, let me just share our today's all right. So let's have a look at our chapter. Let me continue with this recording. Yeah, I'll start to record our lecture now. Okay, right. So it's chapter 4, module 5, STP concept. We start with the intro first, right? So let's have a look at our overview. Right. So here you can see that there are mainly about 3 sections in this chapter, right? So the first one is getting to know what is STP actually, right? What's the purpose of STP? Why do we have STP in our LAN? Okay, so we don't have STP in a wide area network because routers operates on layer 3. Okay, so layer 3 is easier to handle what we call loops, right? Okay, you'll hear this topic again when we reach there. But basically, loop is something that is bad happening in our network, right? So simply means that the flow of the data being transmitted within the network, right, flows in a loop, right? So that is bad because it never reach destination. So it hangs around in the network, taking up space or bandwidth, right? And when you get more and more data flowing in a loop, then the network becomes saturated, right? Now, for layer 3, there's no problem because there's a way, there's a mechanism, right? If you still remember, in layer 3, the IP packets header, there is a field called TTL, time to live, right? So the time to live basically is a timeout. Okay, it's a timeout, right? If you recall that the value within the TTL field is decremented by 1 every time it goes in between hops, right? When it reaches 1 hop, it's decremented until when it reaches 0, then that packet is dropped. So the flow in a loop kind of packet forwarding is not a problem in layer 3. So that's why in the wide area network, we don't have this kind of problem, right? But within layer 2, where in a LAN, local area network, right, the flow of the data, okay, is basically happens at layer 2, whereby we are using MAC address. So the frame header does not have this feature like TTL. There's no mechanism. So we have to do something about this lah. So the something is STP, right? So just remember that STP is a protocol that only runs within local area network, right? So we'll explore, okay, how can it form, okay, inside the LAN, and exactly how STP can alleviate this problem, right? So the second step is to understand how does the STP works step by step, right? What happens, step one, step two, and so on, right? Now, it's important for this chapter for you to know not only the uh, reason why STP is used, but also its operation, the STP operation itself, right? And then we see that how STP has evolved until currently, okay, its implementation, right? So this chapter runs across two lecture, which is today and tomorrow. So we'll do half half, right? So maybe later on the tutorial, if we manage to complete until the completion of the operation, then we'll do until there. If not, then we'll just do partial against last time, the tutorial, partial tutorial only. Okay, right. So those are the three topics. Okay, so we start off with purpose of STP, right? So let's have a look on your slide. Right, so here we already mentioned, okay, the loops can form within a local area network because local area network deals with layer 2 traffic. That means we are using frames, right, to look at the data in terms of frame as a PDU. So frames, as you know, the header, right? We know content of the frame header is scrutinized by the switch. Switch is layer 2 device that looks at the frame header. Unfortunately, for frame header, there is no mechanism like layer 3 where there is something that can alleviate this looping. That means even though the physical network may create in layer 3, in wide area network, may create a loop, but the the flow of data will not stay in that kind of loop infinitely. Yeah, because of the TTL field, okay, it will be removed. Okay, but for layer 2, unfortunately, it doesn't have this mechanism, right? Okay, so in the first place, why do we create a topology where it involves creation of loops, right? Because the next thing we can ask ourselves is, okay, if loops are bad, then when we create the topology of the network, okay, why don't we avoid having loops altogether? So then there's no problem, then we don't have to have a solution because in the first place, there's no loops. Okay, but um, there is one factor called redundancy that is actually very important, very good to have in a network, right? So redundancy simply means you have a backup path, right? Okay. Remember that the internet, for example, is a wide area network, right? It was built from the beginning to be kind of mesh network. Means there are multiple paths from one host to reach, or sorry, from one LAN to reach another LAN, network to network, right? The more path you have as alternate path, the better, because then it becomes resilient, right? Resilient. Uh, a path that is down will not cause the whole network to um, have a severe, connectivity problem. Simply the alternate path is taken, then our data still can flow within the network. So it's similar within a local network. If you want to create fault tolerant or resilient network, then we have to provide redundancy. So that means if one path is down for whatever reason, there are alternate paths that you can basically allow the forwarding of the frames.
Oh,
Okay?
so the redundancy is just extra path just in case something fails.
Yes, exactly.
Uh,
Exactly. Right? If you only have one path, if that path down, that's it, no? Your network cannot function anymore, isn't it? So redundancy simply means alternate path. So the more alternate path you have, of course, more expense. You have to come up with the budget lah. But sometimes because of criticality of the network, that means you really need the network to be up, or else your work disrupted, right? So you want to put at least one alternate path, or if you can afford it, more, right? Now, problem with this is that the possibility of creating a loop, right? A loop basically is a circle, creating a situation where there's a circle in the network where you know frames can go round and round and round and never leave the circle. Can happen, okay? Can happen. So that's why we need to have a way to provide redundancy, alternate path, but still we want to avoid also at the same time the loops. Okay. All right. So because the protocol for the frame header is already fixed lah, right? And they don't want to disturb that anymore. Okay, because there is uh, a function within the layer 3 for wide area network where the router looks into the layer 3 header. It sees the TTL field. The TTL field is a value there, and every time your packet pass by a router, the router will reduce by a value, by one value, by one point, one digit, the value inside the TTL. So as you go down and down, even though maybe it's flowing, maybe there's a network problem, configuration problem or whatever, and so your packet go round and round also. But it's in the wide area network in the internet. But because of the TTL reducing until zero, okay, when it becomes zero, if the router sees that the TTL is zero, the router will not forward anymore. The router will simply drop that packet. But the same thing cannot happen in the local area network, because local area network, the frame doesn't have this feature. Switch doesn't have this feature. It's not part of the protocol, basically, right? So rather than trying to force something like in the layer 3 into layer 2, okay, that means duplicate it, then we have this. So the switch, okay, all agree to use STP. STP is a protocol also, right? And the protocol basically, we'll talk about operations later, in the second section, right? So you can see here, it says redundancy, eliminate single points of failure. Exactly what I mentioned about the single path, right? Single path, the path down for whatever reason, then network cannot flow. Okay, there's no network functioning anymore, right? So if you want to have a like 24 hours kind of 7 days a week kind of operation, then you need to design it so that you have an alternate path. So here you can see having alternate physical path for data to traverse makes it possible for users to access everything lah, the resources within the network. Okay, and it's resilient because if one path down, while you fix that path, there's an alternate path, and so no disruption lah, right? Okay, so your users don't not even aware. This if you use STP, okay, to prevent the loops, it can be transparent, okay, because the switch automatically reconfigures, okay, based on the STP operation, okay, right. Okay, so again, this redundancy of alternate physical path causes loops, right? Right. So this is the thing that STP prevents, and this is what we want to learn about how this STP works, right? So here's the example that where a loop can create inside LAN. Okay, imagine you have two switches. If you don't have switch 3, basically to go to PC4, right? This trunk line between S2 and S1 or trunk link needs to be on all the time. So whenever there's a disruption between S1 and S2, that's it. There's no communication can happen between the segment of the network involving S2 and the segment of the network involving S1. So, right, um, you say that, okay, if I put in another switch, S3, so that means there's alternate path. So if trunk 1 is down, then trunk like the flow of traffic can still proceed via trunk 2 and trunk 3. Okay, so there's alternate path. Okay, and vice versa, right? However, you can see that it's very easily we can see a circle. A loop can form between S1, S2, and S3. So if the data flow does not escape this loop, then of course it will take the bandwidth, it will take the bandwidth, and it's accumulative. Okay, accumulative means when another frame gets trapped into the loop and it keeps circling, and then there are two frames now taking up the bandwidth, and so on and so on until, right? Until nothing can be done. Basically, your network stop functioning because there's no more bandwidth left, right? There's no more bandwidth left, then and it can happen very quickly because the flow of the traffic is very fast. Yeah. So spanning tree protocol at the end of the day is we want to prevent. Okay, physically, how can we prevent? Well, basically, don't have the loop, right? Don't have the loop. Okay, you can see that the physical link is still there, right? When STP is running, okay, STP will maintain only one link, trunk 1, basically, right? Okay, later we'll see by what process does STP decides which path. But so from here, this example, you can straight away see from your rough estimation that trunk 1 is actually the fastest path because it just go from S2 to S1 and then go to that S1's network segment. Whereas trunk 2 and the other path is that you have to travel 2 trunks, right? So there's like a bit of latency over there, right? Okay, so you can see from there the process of choosing which path the STP would choose is going to involve some kind of matrix. Okay, matrix to know which is the best path to keep alive. So what about, let's say you choose already, STP choose trunk 1. So what about trunk 2 and 3? STP will shut it down. Okay, STP will shut down this path, right? So then you ask, so where's the redundancy if you switch off the trunk 2 and 3? Well, it's only temporary, right? As long as normal operation is happening, trunk 1 is alive. That means data can be forwarded between S2 and S1 via trunk 1. Now, as soon as the trunk 1 there's a problem and it's down, the switch will then renegotiate. That means STP kicks in, then the switch will decide. The switches, okay, the switches will decide. Hang on, trunk 1 is down, so we'll have to find if there's any other route, and they will find out that, oh yes, there's this other route that I've disabled earlier on, but now since trunk 1 is not there anymore, trunk 2 and 3 can be safely brought up online, right? So automatically the switch will then bring the trunk 2 and trunk 3 path, alternate path, online. Then traffic can start flowing again, right? It's slightly longer, right? A little bit of more latency, but at least the trunk one can be bypassed. Remember, but trunk one is the one that is down. So data path will now be trunk 2 and trunk 3. So this alternate path will be activated, right? So it's logically blocked because the physical path is still there, whether the STP is using trunk 1 or trunk 2, 3. Okay. Okay. When it says we shut down the trunk 2 and 3, it's only logically through software. We cut off access, the switch cut off access for the path involving trunk 2 and 3. Only when trunk 1 down, then the switch will recognize this and activates the trunk 2 and 3 to be up, and then traffic will flow over there. So at the very basic, this is what's happening with STP, right? What we're going to look at in the operation is the more detail. How does the switches one decide that trunk 1 is the best to switch to keep alive in the first place and shut down to 3? Second, if trunk down, then how does the switch know that trunk 2 and 3 is there and then activate trunk 1? Because you might have more than 2 paths, right? You might have another path, another alternate path, okay, in a more larger network. Larger in the sense that local area network can be large, right? Remember, we can segment it VLAN and all these things. Large network, you can segment like that. So here we're talking about physical link, right? Physical link that we can activate and deactivate depending on the situation of the network, right? Okay, so far so good. Are you okay? Are you guys okay?
Okay.
Okay.
Okay, all right. So we continue, yeah. So the when trunk 1 is down, okay, what I mentioned, trunk 1 is down, so recalculation is happening. This is the STP operation, right? To recalculate. Okay, the recalculate basically just figuring out again to reconfigure again, right? Whenever the current setting is disrupted because of maybe down, like trunk 1 down, then it reconfigures itself again. Okay, and then if trunk 1 up again, right, STP will reconfigure again, right? It will not allow loops. Okay, this is how the STP works. Right, so issues with redundant switch links. So here we delve more deeper into the problems with redundancy, the redundant switch links, right? We already talked about having redundancy. Well, if you don't STP, then you have loop problems, right? So whenever a layer 2 loop happens, what actually is affected is the MAC address table. It keeps being updated. It never settles down. So it never settles down. The switch always try to remember what happens when the switch doesn't know how to forward. What happens if the switch doesn't know how to forward? It doesn't know which port to forward because it doesn't have the info inside its MAC address table. What happened? What does the switch do to the frame? You remember the mechanism?
Broadcast.
Yes.
Yeah, the broadcast.
Yes, it broadcasts. So when the MAC address table is not stable, meaning to say it never settles down because of the loop, it keeps, it gets confused, right? So it starts broadcasting and it make it even worse. Okay, something called broadcast storm will happen, right? Broadcast storm is simply suddenly you get the network is flooded with a lot of broadcast frames. So your link becomes saturated. What does it mean, saturation? It means that your bandwidth is gone, right? Because there's so many frames being transported that the bandwidth. It's something like this. Let's say you have Unify. You basically have very good connections because you you subscribe for 100 megabits per second. But you know that once everybody in your household start using the unified link, right? One person is downloading, one person is streaming, one person is whatever, right? So you know the bandwidth from 100 megabits per second gets slowly taken up by all this network usage, because packets flowing, right? And you find out that, oh, after after all your, especially evening, like everybody home already, everybody using internet, streaming this and that, downloading this and that. Then you find, oh, when you try to use, you test speed test.net, right? You only left you from your machine is only 10 megabits per second. Still okay lah, but from 100 to, because the bandwidth is taken up, right? So this is what happened when the link is saturated with all these broadcast frames that just simply cannot leave the network, cannot go to intended host, just circling there, looping there. Then suddenly the bandwidth just reduce, and it never stop because the loop is there physically, and then logically it's also there. Then there's no way for the frames to be forwarded. Then it's remain in the loop, infinite, looping. And the more frames taking up your network, in the loop, then your switch is working extra hard. That's why it says high CPU utilization. Means there's so many frames. Every time there's a frame, means your switch have to do something, right? You have to check and then make forwarding decision. And this is actually using up the CPU inside the switch. So that's why link saturation means a lot of bandwidth is being used, a lot of frames flowing there. Then and it's not through communication at all, it's through broadcast talk, because one broadcast getting more broadcast, and then not only that, link saturation, but your switch is basically high CPU utilization. It's working extra hard, right? And sometimes those that finally get sent to the end devices like hosts, but because there's so many already being gathered in the loop, and sometimes, okay, through maybe luck, the updated MAC address table suddenly got can check the port. Remember, it's unstable. Means it keep changing, it keep being deleted, keep being created the entry. But once in a while it gets sent. So the probability of a host getting the broadcast frame is actually quite high also. So you find that not only the switch have to to perform this switching, right? So it's high CPU, but also the host, right? The host need to check when it receive a broadcast message. Every frame it has to check, because it needs to know, is this frame directed towards me, sent towards me? So in order for that, it needs to open up the frame header. Means it needs to process the frame. So that means your host CPU, right, will also be involved in a frame processing. Of course, that's why some of these are being offloaded from CPU, like the better NIC collaborating with the Intel CPU, some Intel CPU. I think modern Intel CPU has a hardware-based frame processing, right? That's why it says, oh, if you use Intel chip, your internet will be faster. You'll be wondering, right? Why is that? How come my internet faster? But what has it got anything to do with my CPU? Well, they know that in modern times, everything is connected. Your machine definitely going to be connected to some kind of network. Therefore, a lot of times you need to process frames, right? Now, if your network interface card is not the high-end, so usually your CPU handles it. So to help your CPU, maybe the Intel create a system on chip, right? Some kind of hardware circuit just to help process, okay, offload the execution to check frames and to do networking, processes lah. Okay, but still, if you receive too many frames, even a powerful machine can slow down because of too many frames. It's kind of like the distributed the DDoS attack lah, right? Remember, we send so many requests to the server until the server cannot handle, for example. So it will result something like this lah, right? Right. So of course, network becomes unusable after that, right? And then everything gets lagged down, slow. You can't really send anything into the network or receive anything from the network, right? So one thing to remember is that layer 2 Ethernet, that means layer 2 in the OSI, no, this one is TCP/IP, right? TCP/IP does not include mechanism that can recognize that the frame is involved in a loop, right? So it cannot eliminate those frames from the network. That's why it can potential to keep on looping forever is there for those frames. Okay, but you can see here, this explanation here. Let me just point it right here. This limit the number of times a layer 3 network can transmit a packet. This is what I was talking about, the TTL, right? The TTL field. You can see it inside the layer 3 packet header. It stands for, it's an acronym for time to live. Okay, so let's say the time to live you set as 5. Then after 5 hops, the TTL value will be 0 and it's dropped. So that means even if it involved in a loop, it's only five times. Then it just after 5 hops between routers, then it is dropped. That means it gets eliminated from the network. Okay, for layer 3, layer 2 does not have this, so that's why we use Stp. Right. Right. So you can see here it discussed here. Okay. So far, okay.
Yeah.
Okay.
Do you remember the TTL? We talked about it in our first network course. Not sure.
Yeah.
TTL, I'm not sure. I remember.
Yeah, TTL is a field inside the packet header, layer 3. Okay. Time to live.
Oh, okay.
Yeah. So not sure. I think your first course NetAcad, I think already expired. Is it? If it's still there, you can still refer back. But just type TTL in Google, then it will tell you what is TTL. What I mean by TTL. But TTL is just a mechanism to handle it in layer 3, the loop. Whereas layer 2 in the LAN, they don't have such thing. Okay, that's why we have what we have is Stp instead. Right? Right. So I was talking about broadcast frames. Now you just remember that in LAN, broadcast is very common, especially for something called ARP. We also already learned ARP, Address Resolution Protocol. Remember, if you want to communicate between 2 hosts, yes, you need to know the IP address. Okay, but usually you know the IP address, but you wouldn't know MAC address, right? The thing is, we are not required to remember MAC address. If we don't know the MAC address, how can we send our message to that, even though we know IP address? Because inside the LAN, we use MAC address in the switch. Okay, even though we humans know, okay, that PC is IP is this, but the switch doesn't look at IP. It looks at MAC address. So if how does our machine knows MAC address, right? That's why ARP comes in. Remember, ARP is basically if your computer, okay, do not have the MAC address of the target computer, it will send an ARP broadcast. It is a broadcast because since you don't know, you send to all the hosts inside your LAN. And the host where it matches the IP address will then return back reply. So when it returns, it will have its own MAC address in the frame. So then you know. Then you get it, then you can get the destination MAC address, put it inside your sender MAC address, and you can put it inside your destination MAC address, and you can send off your packet, right? Okay. So the thing is, when you broadcast, when it goes to, let's say three switches, broadcast to switch 1, right? And from switch 1, of course, it will broadcast, right? From switch 1, it will go to two places, switch 2 and 3, right? And from switch 2, it goes to switch 3. But from switch 3, if you broadcast to switch 3, it goes one to its segment LAN, but it also send back to switch 2. Switch 2 don't have, it will broadcast back, right? And then switch 1, if at that time haven't updated, it will rebroadcast again. So it keeps broadcast, right? So you can see from there, the loops can happen, right? Now another thing that can cause the loop is multicast, right? Multicast in a LAN is actually transported as broadcast. Only IP version 6, right? IP version 6 will, when you multicast using IP version 6, it will use multicast in layer 2. Okay, in IP version 4, I think multicast in the layer 3 will be in the layer 2 will be transported as broadcast. Again, then of course it will create loops, right? Unknown unicast frames simply means if you send a unicast frame where the switch doesn't have the information in the MAC address table, what happens? And it will broadcast. And then broadcast is happening again, right? So you can see those possibilities that can cause whenever you have broadcast. So as long as you have potential to have a broadcast, then the loop can happen, right? But of course, broadcast is a normal thing in a LAN, especially with ARP. Multicast only when you do multicast, right? Unicast is when you don't. Yeah, unicast also can happen when the MAC address table is not fully formed yet. This is dynamic, right? Switch will dynamically create it, right? But ARP happens all the time, right? Right. So you can see when a loop occurs, you can sort of do a thought experiment and try this. But doing using packet tracer, you can simulate this, right? Using packet tracer, you can simulate. You create the loop without STP. Hang on. Can we disable STP? Because STP is in modern switches, it's enabled by default. So I think you can go into iOS and disable it, which is just to see, right, what happens. Okay, you will see the loop happening, right? Okay. All right. So yeah, I've explained all this. These two already can. This one is when the MAC address table is not complete yet. So that means the switch have to broadcast, right? So and broadcast again will cause loops. So I talk about broadcast storms now. It's just that one broadcast go to another switch. That switch creates another broadcast. It goes to another switch, create another broadcast, and maybe the broadcast eventually go back to the original switch, and then it continue broadcast again. So it means an avalanche, keep build up the broadcast. I think it can be if you look at if you try to plot it using a graph, I think it's kind of logarithmic kind of graph. Okay, just double very quickly, right? So you can see there, broadcast storms can disable network within seconds, right? Because it is logarithmic kind of if you plot the increase in the broadcast, okay, sort of like landslide now. Okay, some small thing can just create a very large avalanche very quickly, right? So same, we call that a broadcast storm, right? So it's mentioned here that it can also be caused by hardware problems such as faulty NIC, right? Okay, but most of the problem from broadcast storm is created by layer 2 loop, right? Faulty NIC, I think for modern network card is not really, because it's not is standard, right? It's very difficult for you to find a faulty NIC, right? Seldom for me. So usually the misconfiguration, if you don't STP, then layer 2 loop happening cause the broadcast storm. And when broadcast storm happens, right, there's nothing to dissipate it. It will keep on happening more and more and more and more. So that's straight away your network is overwhelmed, means nothing can flow already, right? Unless you reset the whole thing. Okay, right. So I talk about ARP requests. Very common because ARP request is very common in a LAN, right? Very common because ARP basically, if your ARP table inside your host gets deleted, or if you just connect to the network, so you don't have the information, the MAC address info of other hosts inside the LAN. Now I just want to share. Let me just open. Let me just temporarily share this one first for you. Right. So what you're seeing is a terminal on my computer. So I'll just type. If you recall, we just type RP, I think A, right? Then you can see what I mean. What is a RP table? Every host has this. Okay, this is maintained automatically by your OS. Okay, and this table is dynamically created when you set it, when you're trying to send a packet to a host inside your LAN, and it doesn't exist, the mapping between the IP address that you want to send to and the MAC address does not have an entry inside your ARP table. What happens is ARP broadcast is sent out, and then when you receive the reply from that host, because that host will reply, the other host will not reply. Your target host will reply to you, then your OS will update, and then finally can send your message. Okay. Now this ARP table is dynamically created. Now sometimes this become in a more static LAN, this probably won't change a lot, right? Won't change a lot. But in a typical LAN where people can plug in, switch off and on, right? And this is not also permanent. Sometimes OS has a decay rate whereby after a certain period, it does depend on the OS, this information becomes stale. So then it will try to update it, right? Because you can never say, oh, I got this and it's fixed, forever fixed. This will be that PC connected to that IP, right? Because we cannot assume, right? Most of the time, yeah, of course, static IP the administrator will give a static IP to a particular PC. But we also realize that sometimes we allow DHCP. So if DHCP, even with wired, not only wireless can have DHCP, wired also can have DHCP, where the IP address is dynamically given to a computer, right? So in that case, the mapping between the IP and the physical address is not permanent. So that's why the OS has a way to decay this information, in the sense that after a period of time, your trust on the mapping is no longer 100%. So you might want to update again, or forget about it and get back to rebuild your table, right? So this is the
The OS refer which one?
Sorry?
The end device. The OS.
Yeah, OS.
Okay.
The OS is handling the ARP table. Every end devices, every host lah, right, in the local area network will have their own ARP table. Because although if we want to communicate from the point of view of user, we're using this IP address. Okay, on the internet networking, fine, IP address, because router forwards based on network address that extracted from IP address. But inside LAN, okay, the switch does not read the internet or IP address. What the frame looks at is physical address, right? Physical address is the MAC address. So the ARP is a way to translate, right? If you have the entry already, fine, good. If you suddenly say, I want to send a message to IP address 224.0.0.22, what happens is the network stacker will try to find an entry here. Oh, okay, I need to fill up the destination MAC address, because your switch is going to look for that instead of IP address. Do I have this info? So you scan, the OS will scan through 224.0.0.20. Oh, yes, this is the equivalent MAC address for that IP address. So this MAC address is then put into the destination MAC address of your frame of your data, right? So in layer 3, you have this IP address. In frame, you have frame header, you have that MAC address. But what if your table is not complete yet, because you don't have this entry yet? What are you going to put inside your frame destination MAC address? Must be, you cannot leave it empty, right? So no choice. Your OS can send a ARP request, which is broadcast. Since you don't know, you don't know, so you broadcast inside your LAN. Only the PC that when you receive it, it sees that the IP address belongs, that means destination IP address belongs to it. And then it will reply, ARP reply. Of course, the process of sending back a reply means the source MAC address is sent together, right? So when the reply reach your PC will open and check. Oh, okay, I know already what is your MAC address. I look at the source MAC address, I know. So I update my ARP table, right? And then from there, I continue. Then I can send to you, right? Now my destination MAC address, I have already gotten from you. I put inside my destination MAC address. So the switch now can do the forwarding, right? Okay. Now that ARP broadcast is happening. It's a normal happening that inside a LAN. Okay, and this is one of the cause for broadcast storm. If you don't have STP, if you have redundancy, okay, it can flow in a loop. Right. So this is what we mean by this one. Let me just yeah, this part. Right. right? When you says here, ICMP neighbor discovery is a protocol within IP version 6. ICMP version 6 is part of IP version 6 protocol, right? So you can see IP version 6 packet never forwarded as layer 2 broadcast. They use neighbor discovery, right? Neighbor discovery and neighbor discovery protocol use layer 2 multicast. All right, so a host caught in layer 2 loop is not accessible to other hosts, meaning to say once the host is involved in layer 2 loop, because it sends out RP, it probably will not get a reply, right? So means it's inaccessible. Okay, so basically it seems like offline, right? Okay, so the broadcast storm and the loop causes the switch to keep updating its MAC address table. So that means constant changes here means it never stabilizes. Okay, so it keep changing due to how you receive a broadcast, you receive a broadcast, and never update lah, because it just keep coming a broadcast coming from the other switch, and then it's never updating its how to say the let's say the target host MAC address. So it itself will participate in broadcasting, right? Right. So without any updates uh, that's supposed to happen in normal operation, okay, happening to its MAC address table, then it will never know how to forward the unicast frames. When it doesn't know, means it will keep on broadcasting. That's why broadcast storm can happen, right? Broadcast keep on happening, right? So it says here to prevent this issue, that's why we have spanning tree, okay, spanning tree protocol, okay, and it's activated by default, okay, to prevent this layer 2 loops from happening. All right, so STP is based on an algorithm invented by Radia Perlman. Okay, so I just want to share with you guys Radia Perlman. I think I have that. Just in case you're curious, to find more about it. Screen tree, so screen tree is all right. Okay, so just show you. So this is you can get it from this ResearchGate link. I think this lady is still here. Yeah. So this is the title just now mentioned. So I'm just going to share you here so you can just download the PDF here. Right. So the PDF is basically just this, right? I think it's an easy read now, right? Talking about the protocol itself, right? This is the original paper, right? So it's always like this in computer science, yeah, right? If there's a problem, someone will come up, say, I got an algorithm how to solve that. Then they present the paper, and if it's accepted, people think, oh yeah, okay, your technique is good. Then they implement, and you'll be surprised suddenly, it's implemented the whole world, or as a protocol, becomes very important protocol. Okay, this is very 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 normal happening in computer science, just to let you guys know. All right, so do go and try to download it, and when you're free, just have a read, right? So right, so her spanning tree algorithm, or STA, right? The algorithm is created by her, and it's appropriated, okay, to create a protocol. So algorithm and protocol is slightly different. Algorithm just talk about the algorithm. What is the technique? How can we solve this problem? Then when you take that solution and then you implement it as a protocol means step by step how you're going to implement that algorithm so that there's a switch, right, can basically follow that steps. Okay, and when they follow that steps, switches follow that steps, then you don't have this looping problem, right? So protocol simply say that all the switches must know this and must follow this technique, right? That's become protocol. Okay, so the main idea is that you select a single root bridge. Now, this is legacy, right? Legacy before modern times where we call this the switch. Okay, the old name for a switch is a bridge. Why a bridge? Because you see what does a switch does? Switch connect a group of computer with another group of computer, right? And that idea previously is when you put an intermediate device between this group of computer and this group of computer, you form a bridge between them, right? Okay, this is a time when before switches, networks segment of networks are actually Ethernet bus. You know, those single backbone network, which is not switch based. It is actually contention based. Remember that one single backbone, all the computers, right? So last time, okay, I want to connect these two segments. This backbone, they have their own computer. This LAN connect, right? But not like a forwarding in a router layer 3, but still layer 2. So they have a device called a bridge, right? Just to connect this LAN and this LAN so they can communicate. But over the years, that bridge now they start evolving its functionality. So instead of having a Ethernet bus, they just straight away wired all the hosts to the switch until we get the modern switch. So that's why you can see that the bridge name there. Actually, right now, when we talk about bridge, we talk about switch, right? But the name state when we are discussing this algorithm, right? So the main idea, select a single root bridge means the what we want is the root switch. If you have many switches, which one is the root switch? Okay, so okay, I don't want to confuse you, so I just follow the text. I say bridge, but in your mind, translate that, oh, switch. I'm talking about switch, all right? So select the single root bridge. Later we'll see in the operation how to select that root bridge. How do we know that bridge is the one is the root bridge? Okay, we'll learn it in the operation, right? Right. So basically, the selection of the root bridge is determined by least cost path. Least cost path. Remember, the operation is we want multiple path, but to prevent loops, because we don't need multiple path, okay, all at once, isn't it? In fact, it's perfectly okay if we remain one path and the rest of the path we disable until this one go down and then we enable whichever path left. Then that become alternate path. Meaning to say there is no need to get all the alternate path up and running at the same time. That's the idea. Okay. While the selected least cost path, least cost here simply means which one is the fastest way. Okay. The backup way we prefer it to be the slower path lah, because it goes like, not straightforward, right? So we look at all the alternate path. Which one is the fastest way? We make that as the main path, and then logically block all the other path. Make sense, right? Rather than you select those longer path. The cost here means cost of traversing the network. We want to select the fastest way as the main path, right? And then the rest we just disable first, because still we don't need it. Okay, unless the main path is down, then we go back to our alternate path and reselect which one is the, between the alternate path, which one is the least cost path among them. Then that one we bring up, the rest we logically block again, right? So we keep doing that as long as the path is still available, alternate path, and then as long as the path, current path is down, then we elect again, and then choose the path, elect. These steps are more detailed in the operation section later, right? Okay, do you guys get the idea of STP for now?
Yeah, a bit.
Yeah.
A bit lah, yeah.
Okay. So I purposely make it a very general, the explanation, so that you get the main idea. Right, before I move forward, I just repeat first again. Okay, so that we have easier for us to remember the steps later once we understood it perfectly.
They automatically
Mm.
open and close the path.
Yes.
Not
Right.
not us now manually do. I just let the STP.
Yes, the STP
do it
protocol
for
will
us.
do it. And there's to make it a little bit more detailed, the protocol needs to switch. The switch needs to choose which path to make the main path, the rest block first. Okay, so the idea is, of course, logically, the main path you want to choose to be the main path is the fastest path, or in network speak, least cost path, right? And then the rest you logically disable, because physically they're still connected. We just make it down. When it's down, then the network cannot see that there are alternate path, then you cannot form the loop, right? Now, redundancy is when the main path chosen is down, right? Now, the switches have to, again, redo the whole reconfiguration, means the step again, to choose among all the alternate path, which one it becomes the main path. And you always choose the least cost path, try to choose the least cost path, right? And then that one is brought up, the rest remain down. So this is the idea, right? And later we'll see that how do we know which one is least cost path, right? And how do we know that how do we select if two paths the same cost? What is the how to break the point lah? That means if you have two or more path, they all have the same cost. So then because automatic, right? Automatic, the switch have to do automatic. So how do they choose, right? So that is part of the later the algorithm you see. Right. So here you can see that the main ideas, right? Main ideas. We're not yet saying, okay, this is the step 1, step 2, just the basic idea first, right? To introduce it, because after this we are going to go to the next section where we actually look at more detail the operation. All right. So how does the spanning tree algorithm create a loop-free topology? Again, it involves selecting a root bridge, which is the switch, is the root, right? Because what is important, that bridge becomes the reference point for the LAN. right, for that LAN, so that we can create a spanning tree. Okay, spanning tree, there's branches, there's a root, there's a branch, there's branches, right? And the branches just go from the root to the end. It does not create a loop. Okay, and this is the idea. We don't want to have a loop. Okay, so but we need to know where's the root, right? Where's the root? Like a tree, where's the root? So we need to know where's the root bridge. Okay, later we'll find out how do we select the root bridge. I mean, how the switch following the protocol select the root bridge, right? And then another idea is to block the redundant path. Okay, redundancy is created by having it ready as physical link. But in the meantime, to avoid loops, after we select the active path, we disable all the redundant path to ensure there's no loop, right? Okay, this second idea, that block redundant path. Thereby, following this, we will create a loop-free topology, right? Loop, that means it will not create a loop, because once you block the redundant path, right, means nothing can pass through it, then it cannot form a loop anymore, right? So for example, if this is a loop, right, the switch being here, here, and here, right, and then this one go here, and then, you know, so if we determine that this is the main path, then we block this one, then no way it can create a loop anymore. But then in the meantime, we can use this path, right? Can use this path. Okay, this is what we mean by loop-free topology, by blocking certain ports. Right? Now, if this fail, we know this link, this alternate link here is just logically down. It's not damaged or whatever. It's not faulty. So if the main path fail, we recalculate, we redo again the which path, here it's a single path, so it's easier to decide, right? Recalculate in case of link failure of the main path, right? Okay, so this is the basic idea, right? These four are the basic idea in the spanning tree algorithm, right? Right, so I'm going to let you guys let me see. Okay, guys. This one, yeah, this one. Right, so I'll let you guys listen to this first.
The spanning tree protocol is really useful when you want to have redundancy in your network. You want
Can you hear the voice?
Can.
Can, all right.
to have backup paths, backup links, backup switches, but this causes potential loops in the environment. In this case, the spanning tree protocol has recognized there's a loop in the environment and it's shut down one of the links. This is what we want the spanning tree protocol to do. So right now, when PC1 pings PC2, it takes that pathway. Now, what if the link goes down between S1 and S2? Well, in that scenario, spanning tree protocol will recognize that the link is no longer there, and then it will take that blocked port and change it from blocking to forwarding, and now we have our alternate path to reach PC2, and redundancy has been achieved. Now, what happens when we don't have spanning tree protocol? S1 will forward a packet to an unknown destination out of both ports, except for the one it came in on. The packet will reach PC2, but notice that S2 and S3 are similarly forwarding the packet, and the packet is going around the switch network. A second version of the destination packet hits PC2, even though it already got the first one. Notice the packet's going back to S1. S1 is now getting false information into its CAM table as to the location of PC1 and PC2. PC1 receives this packet that it sent to PC2 back at itself, and the process begins again, duplicating on the network. PC1 and PC2 keep receiving duplicates, and S1, S2, and S3 are confused as their CAM tables continue to fluctuate, causing an instability in the MAC address table. This will eventually shut down, essentially, communication on the network, causing a layer 2 broadcast storm. This is what happens if we don't have the spanning tree protocol. If we turn the spanning tree protocol back on, order is restored, redundant links are blocked, and we have a path through the network. Okay, let's test this out on a live network. I set up my home network to mimic the topology for the spanning tree protocol. I have 3 switches that are connected to each other, creating a loop or redundancy in the network. I'm located at PC1. I also have a console connection to S1, and my IP address is right here, 192.168.1.100. I connected a second PC to switch 2, and it's located at 192.168.1.101. Now, S2 is the root bridge, and therefore S1 has an alternate port in blocking mode right here. Let's take a look and verify what's going on. And then what I'll do is I'll disconnect the Ethernet cable connecting S1 and S2, and we'll see if the spanning tree protocol will recognize the broken link and then reactivate and take the blocking port from blocking to forwarding, thus adding redundancy and allowing the packets to travel across the network. So let's verify, first of all, that everything's working. All right, here's my command prompt, and you can see that I can ping PC2 at 192.168.1.101. Also, I have a console connection using PuTTY. Let's see here. I'm in S1 right now, and I'll type enable. And then I'm going to put in the command show spanning dash tree VLAN 1. And when we do that, you can see that the root ID and the MAC address of the root bridge, this is not the root bridge. This switch has port 2 in the alternate role in blocking mode, or the status is blocking. So I am the switch here, S1, and this port is blocking. Now what I can do is I can telnet over to the root bridge, the boss switch. We'll telnet over there, and we'll verify that it is the root bridge. And you can see it says this bridge is the root. I'm in S2. All right, so what I'll do, notice all ports are in forwarding mode. All right, I'll exit out and go back to S1. So now what I'm going to do is I'm going to disconnect the Ethernet cable connecting S1 to S2. All right, there goes the cable. And you can see that a link just went down. So we'll do a show spanning dash tree VLAN 1, and you can see that we've lost a switch port. And notice this is in learning mode, status learning. So it's changing from blocking, notice port 2, to learning.
Recalculating.
And if I put the command in again, now it's forwarding. And now I should be able to ping PC2 once again. And I can, except this time, the path that it's taking with the broken link is this way.
So means if the first alternate route is down also, it will find the next alternate route.
If you have a next alternate route, yes.
Oh,
It keeps on doing repeating. Yeah. The learning part, just now you saw that LRN, something like that. The status when you show spanning tree in the switch, that shows that it's in the process of recalculating. It's redoing the first operation when it selected the main path earlier on.
When it select the main path, does it usually select the one that shortest distance to the?
Yes, the first time it calculates a spanning tree, when it selects the main path, it already knows the main path is the so far is the best path, the least cost path. When you disable that path, then it will recalculate again. Okay, just now it was simpler lah. There's only one path, so it will just choose that one as the alternate path and enable that path. But if you have multiple, that means you have more than one alternate path, then it will, during the recalculation, it will find out which one amongst the alternate path is the least cost path and make that as the that means it will select the root bridge, and then the port going to the root bridge will be open, alternate path, and then the other port going to the another alternate path will be closed, right? This is the thing. That's why we need the root bridge. Okay, once we elect the root bridge, okay, we means switches lah. The switches will elect the root bridge. Then the port on the switch connected to the root bridge will be open, and the port that is not connected to the root bridge will be closed. Okay, so this is the idea lah. So let me just
The spanning tree protocol is really
sorry, just off it first. All right, so let's proceed after this. Okay. Right, so packet tracer related to this topic, right, is you will create and configure a simple tree switch network with Stp. This is for your revision lah, right? Even before we do the practical on I think Wednesday, you can revise by going through the NetAcad. They provide the packet tracer, so you can download that and just simply follow the packet tracer activity. Create and configure simple tree switch network with Stp. View the Stp operation. Disable Stp and view operation again. This is what I'm talking about. If you want to understand more what happens with Stp and without, right? Remember in packet tracer, right? You can slow down the simulation by going into simulation mode, right? You will see, that means you can then, because the broadcast storm will happen very, very quickly. So you want to slow down, you go to simulation mode, and you can then trace through step by step what happened, right? So if you want to, sometimes looking at packet tracer, playing around with it is helps you understand what's going on easier than just understanding in your mind, right? Okay, so any questions so far?
so far no.
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 Okay, all right. So the next section, right? I may not have. I only have a half hour left, so we might be halfway through, but it's okay lah. Huh? Right, Stp operation. Here we look at the more detail about the election of the root bridge and also the configuration. All right. So let's have a look. Steps to a loop-free topology. Okay, using this spanning tree algorithm, the spanning tree protocol builds the loop-free topology in a 4-step process. This is when we say the recalculation or learning. This is the 4-step process that the switches go through. Okay, switches means all the switch participate. Yeah, all the switch participate. So elect the root bridge. You all will agree which one is the root bridge, right? And then elect the root ports. Okay, from once you know what is the root bridge, you know which one is the root ports, right? And then you will know what is the designated port and what is the alternate port. Now the ports that are going to be blocked will be the alternate ports, right? So within the loop this STA, the switches will make use of something called bridge protocol data units. This is the data units that will share among themselves. You can see that if you use the capture inside your simulation mode, right? You will see this PDUs lah, bridge PDUs. These are being passed along inside the network between switches, and they make use of these PDUs to share information about themselves and their connection. That means what are they connected to and some info. And this info is very important, right? Because this info will help all the switches, because they share among themselves. They will use those information first of all to do step 1, to elect the root bridge, right? You can see PDUs are used to elect the root bridge, then figuring out which are the root ports. They themselves will decide which are their root ports, which are their which switches will have the designated ports and alternate ports, right? Right. So inside the BPDU, there is a bridge ID. Okay, or in short, BID. Okay, this BID identify, because the BPDU will be sent, be shared among themselves, right? Each of them will send their own BPDU, right? And then they will receive other, maybe one switch will receive other switches BPDU, but that switch also will send its own BPDU to other switches, right? So how to differentiate if you receive more than one BPDU? By looking at the BID or bridge ID, right? And this BID is also very important, because not only to identify, but when you want to decide, okay, which of the switch become the root bridge, right? You will look at BID. Okay, and also the ports role means either it's root ports designated or alternate ports. Okay, all this you need to decide which one is which one, right? The info comes from the BID itself. So what is inside the BID, right? There's a priority value, the MAC address of the switch itself that sends the BPDU, right? And something called extended system ID, right? So which switch has the lowest BID value when you combine all three, right? Then that will be considered as the lowest BID value, right? So that becomes if there's a deadlock whereby the lowest costs are determined by the path is, let's say, there's similar, right? That means there's no way to break the deadlock. Then the MAC address, which is unique, right? MAC address is unique, is the info that will break that deadlock, right? Means whoever has the lower MAC address wins. If all else info all being equal, you need to break the deadlock, because you only need to have one root bridge. So finally, it will come down to the MAC address of all the switches, which switch have the lower value MAC address. And you cannot have similar, because MAC address are unique, right? It's unique for each each NIC. So this NIC on the switch is the MAC address for the if you recall, the only way we have an interface, layer 3 interface on the the switch is the management port, and there's a MAC address connected to that. So that's the MAC address of the switch, right? So you can see in the example we had before, right? The root in this configuration, the root bridge is the S1, right? And you can see that the S2 and S3 nodes, basically the S1 is the root bridge. S1 also know that it is a root bridge because of the BID, BPDU BID. Yeah. Then S1, of course, like the example just now shown in the video, if you telnet into it, it will determine itself. Oh, this is the root bridge, right? Now S2 knows which port is connected to S1. S3 also knows which port is connected to S1. So those port that is directly connected to your root bridge becomes the root port, right? On the root bridge itself, okay, its ports become designated port, right? Okay, right. So and then you can see that there's all the steps we mentioned 1, 2, 3, 4. It's all about election. Election because we have more than one switch. So which switch becomes the root bridge, right? And for every switches, which ports become root ports? Okay, the root ports is considered as which one is root port, lowest root path, of course lah, right? And then elect designated ports. Directly connected usually means it's the lowest port, lowest root path cost, because you cannot get any lower than having a direct connection to the root bridge. That's why I said switch 2 directly connected port to the switch 1. Usually that port is root port, right? Because that is directly connected, so cannot have a. If you go to let's say you have an alternate going here and there, let's say more than one alternate port, you have another alternate port, right, which is not directly connected to S1. Definitely that one will be more latency compared to the one directly connected to the root bridge. So usually the one that directly connected to the root bridge usually is having lowest root path costs. So how to elect root ports is the port that is has the lowest root path cost, means the port that goes have a direction towards the root bridge, which has the lowest root path cost. All right, and then after you selected your root ports, and then number 3, you elect again which of your ports are the designated ports. And then number 4, electing. After you got designated, then you know which one of your port is the alternate ports. Right? All right, so okay, so let's have a look first what is the bridge priority, because we mentioned about these 3 things, right? These 3 things formed the BID, right? So bridge priority, extended system ID, and then MAC address. So bridge priority is the default priority value for all Cisco switches, right? And the given decimal value is 32768, right? Now, because they're all have the default is all this value. Okay. Now, even though the switches can arrange themselves, sometimes as a network administrator, you yourself want to identify which one is the root bridge, right? So if you want to bypass the election, straight away you can set the value for the bridge priority yourself. So the one that you want must have lowest. So you can basically have all the rest on the default value of 32768. But you decide, oh, this switch, I want this switch to be my root bridge. Then you configure the bridge priority lower value, right? You can see that a lower bridge priority is preferable. So during the election, right, the ones that have the lower bridge priority will win. Okay, the switch that has this one lower priority, bridge priority, right? If you don't want to do that, that means you just let the algorithm handle it. Then you just leave it at default. Then all the switches will have the same bridge priority, which is 32768, which is the default priority value given by Cisco. Okay. Next is extended system ID. Right. So the extended system ID value is a decimal value added to the bridge priority value, right, in the BID to identify the VLAN for this BPDU, bridge protocol data unit. Okay. All right. So MAC address, this one you don't. It's the same MAC address as any interface. This one burn in from the factory, right? So if you didn't change any bridge priority, same priority lah, 32768, and then your switches happen to have the same extended system ID, right? Then to break the deadlock is the MAC address. Okay, this one you can't control already. Yeah, the MAC address is given by the factory, burn in from the factory. So this one, depending on which switch has the lower MAC address, then that switch wins. Right? Again, combine all this. If you have the lowest value, okay, that means if your MAC address is low, then you definitely you will win among all the other switches. This switch has the lowest MAC address, saying that bridge priority and extended system ID are the same for all the switches. Then the switch with the lowest MAC address will win because preferable is the lower BID. Right? So as an example, let's look at this too. Which is the root bridge? Which one do we look at first?
The priority.
Priority
Right?
attachment.
Yeah. So priority, looking at here, we look at priority first, and then extended system ID, and then MAC address. So if we are given these two, switch 1 has that BID, switch 2 has that BID. So which one will win, become the root bridge?
S2.
Yeah, because we look at the priority, we straight away see that it has lower priority. Right? Okay. Right. So between S3 and S4, which one will win?
S3. I don't know.
Okay, so let's have a look. S3 and S4, we look at priority first. S3 priority is 32769, right? And then we look at S4. S4 priority is also 32769, so equal. So far, no switch is winning, okay? Because they are priority equal. Next, we look at the this one, extended system ID. So extended system ID 32768, 32768. They are both the same, right? So still equal. So far, we don't know yet which one is the root bridge, but there's the MAC address. Because MAC address is unique, they cannot be the same. So that will be break the deadlock. So when we look at the address between MAC address between S3 and S4, which one is lower?
Oh, is it S4?
Yeah, S4 is lower. right? You look at the first hexac, and then you can see as 4 wins, right? So if the question is a question, okay, showing you what, and then they normally will, if the purpose of the question is to ask you which one is the root bridge, so check priority between all the switches involved, then check the extended, then ID, and then check the address. From there, you can definitely tell which one is the root bridge. Okay, right. So here, another example. So STF designate only a single switch can become a root bridge, and it will be a reference point for all path calculation. Right? Switches exchange will be used to build the loop-free topology beginning with selecting the root bridge. So our whenever we are given a topology and ask question, ask you, will always ask you which one is the root bridge. Right? So all switches in the broadcast domain participate. That means broadcast domain is inside the LAN, right? Will participate in the election process. After a switch boots, it begins to send out BPDU frames every 2 seconds. These BPDU frames contain the BID of the sending switch and the BID of the root bridge, known as the root ID. The switch with the lowest BID will become the root bridge. Okay, so at first, all of them declare themselves as root bridge by default, with their own BID set as root ID, right? But after exchanging BPDUs, they will adjust, right? They will compare their own BID with the other BID. Okay, if true, from all the BID they receive, or it's a switch receive, is all higher than, then it will remain as root bridge. But if there's suddenly there's a BID which is lower than its own BID, then it has to relinquish lah. It cannot be the root bridge. Okay, it will definitely elect the other switch with that BID becomes the root bridge. So that means, let's have a look into this diagram. So you can see here, right, the bridge ID, priority, MAC address, priority, MAC address, priority, MAC address. Okay, in this case, you're not given the extended ID, so you just use these two. Right, so without looking at this info, we don't know yet, right? So let's go step by step. S2, 3, 7. Imagine the S2 can get all S3, S1, BID, S1 also can get the rest. All of them can get each other's BID. So S2 has a priority at 32769. This one, S3, 32769. This one is 24577. Straight away, you know which one is the root bridge just by comparing priority. The lowest priority will become root bridge. You don't even have to check the other things. Remember, we check priority first. Okay, so this one root bridge. All right, so let's proceed first. It says here, impact of default BID. Default BID means you did not specify the priority. Means it will be at default 32768 as set by Cisco. Right? So if you did not, enter in your own priority number for which switch, right? Then it is very possible that the switches will have same priority, which is the default priority. So when this scenario where you have all equal priority, you can see here 32769, 32769, 32769. So it's deadlocked. We still don't know which one is root bridge. Then we check MAC address, which one is the lowest. So 0A, okay, make it easy for you. The difference is 22222, 33333, 1111. Which one lowest? This one, right? 000A 001111. So this one wins. Switch 2. So switch 2 become root bridge. Right? Right. So your VLAN assignment is VLAN 1. So automatically your bridge ID +1, right, is your extended system ID. But since your bridge ID is the same, and you're in the same VLAN, let's say all these are in VLAN 1, so it's +1. So that's why we ignore the extended system ID. System ID also will be the same, right? Therefore, to break the deadlock, we look at MAC address. From the MAC address, we see that switch 2 has the lowest one, right? Okay, so switch 2 wins the election. It becomes the root bridge. So far, okay?
Okay.
Okay. In the end, we choose trunk 2.
Switch 2. Now, when we say about root bridge, remember, a bridge is an older name for switch. Okay, so they never updated the name. Okay, I guess they don't want the confusion for the literature. Since all time they call it bridge. So in fact, when we say bridge, it's actually switch. So root bridge means root switch lah, right? So it's actually electing switch. Which switch is the root bridge?
Oh, okay.
Yeah. So here in this first example, by looking at the priority, we straight away see that S1 has lower priority. Can you see that? It's 24577. Switch 3 has 32769, whereas switch 1 has 32769. So switch 2 and switch 3 has the same priority, but S1 priority is different. It's lower. So our preference is lower. Okay? Preference is lower. So S1 wins the election. So S1 is designated as the root bridge. All agree. Okay? They all will agree. So all of them will remove because by default, they all set it themselves as root bridge until they start receiving other switches BID. And they all check lah, right? When they see that another switch apart from themselves has lower BID, then they will remove the configuration as for themselves as a switch. They will remove themselves from becoming root bridge, right? And then the S1 basically the S1 will also read the BID from S3 and S2, and from checking comparing between itself S1 against S3 and S2, S1 will know that S1 has the lowest priority. So S1 will remain configure itself as root bridge. Okay?
Okay.
So this is like implicit. Explicit means, oh, S2 will tell S1, you are the root bridge. No, this one is, they all share the BID and they will use the BID to compare. They have their own BID, they compare with other switches BID. Whoever has lowest BID will become the root bridge. Is it okay so far?
So different switch have different BID.
Yes. Right?
Okay.
And because we check the priority first. If all the switches the same, then we check the extended ID. Okay. Now hint: if they all belong to the same VLAN and they all have the same priority, they will all have the same extended ID, because extended ID is just priority plus the VLAN ID. Is that okay?
can we modify the priority?
Yes, exactly. Just now I was talking about in this here.
Oh, okay.
Right? Bridge priority. As an administrator, maybe you don't want them to elect themselves. So how do you influence the election? You go to your preferred, you as the system administrator, you go to the preferred switch that you want to be the root bridge. You set its bridge priority lower than other switches. Then during the election process, the election process is automatic, yeah. So during the election process, definitely the one you set as the lower bridge priority yourself will win. You influence it already.
Oh, okay.
Yeah, that's how you control, right? Okay, but if you don't want to control, then you leave it at default. By default, Cisco set all switches having I think 32768. So definitely the bridge priority will be the same. Right? And if they're in the same VLAN, then their extended ID, if their priority is the same, the extended ID will be the same as well if they're in the same VLAN. Right? So at the end of the day, you still need to know which one is the root bridge. So ultimately, you will check the MAC address. Okay, when it comes to MAC address, you will definitely find which one is the root bridge. Why? Because MAC address must be unique. So each switch will have its unique MAC address. So among the MAC address of the switches, the one that has the lowest in terms of value of the MAC address will win and become the root bridge. Is that okay?
Okay.
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 All right. Make sure you know, because the question out of STP is very much reliant on you knowing this part.
The MAC address will always be different because there's a lot.
Always, yeah. Because recall from our first course, the introduction to computer networks, can
The priority is easiest to change.
Yeah, MAC address you can't you on the computer you can change, but I think it's not advisable to change. But on the switch, not sure whether you can change or not the MAC address. Because why I say can change, because in order for MAC address to be used, it needs to be loaded into memory. Like anything loaded into memory, you can change actually. Yeah, but then that is more tedious compared to just setting the priority. Right? Priority is straightforward. You just change the priority, and you can then bias the election, right? But if you want to, you're happy to let the election go without any contribution from you as the system administrator, then of course it will be, if they are all the same, like in terms of priority and extended ID, then the deciding factor will be the MAC address law. Which switch has the lower value MAC address, then that switch will win as the root bridge.
So the priority must be a multiple of 4096.
Multiple of, sorry?
4096.
4096. Where do you get 4096?
The previous slide. There it's increments of 4096.
Oh, yeah. That means you if you want to set your own value, it has to be increments of 4096. So let's say 32768. So you want to set a low value. So you subtract 4096. Right? Then you can set that value. That's what it means, increment of 4096. Is that okay?
Okay.
Yeah, you cannot set like, oh, I like the number 32760. Then I want to set, because if the increments is 4096, then that means the next value lower than 32768 is 32768 minus 4096. Okay. All right. Okay, so if this one is okay, so the first thing we already decided, which is which switch, the step one, which switch becomes the root bridge. It's okay, eh? It's okay, right? Yeah.
Yeah.
Okay, so we talk about root path costs, because we want to know which one is the root port, right? On the switches that is not the root bridge, we want to find out which port is the root path cost. Which one is the root port? Okay, in order to to know which of the switch port is the root port, we need to determine this one first, root path cost. See? Okay, so you can see that it says when the root bridge has been elected for the given spanning tree instance, means inside your LAN, you already identified step one, identify the root bridge already during the election earlier on we discussed. Then the algorithm try to find the best path to the root bridge from all destination in the broadcast domain. That means because we want the path that is going to be switched on versus the path that's going to be blocked in order to prevent the loop. Okay, we want that path that we select or the switches select will be the best path. The best path in terms of networking simply reword as the lowest path cost, having the lowest cost. High cost means the latency is high, means it takes longer to reach. If I give you an analogy, like I drive to KK, which road will be the fastest way to go to KK versus which road will be the slowest one? So when we want to find the root path cost, means in order for me to designate one of the port or two of the port, which one in my port in reaching the root bridge will have the quickest path, right? Okay, because makes sense now, right? Because you don't want to use the slow path and then disable the fast path, because then your network will be slow. Okay, you want the alternate path becomes disabled, which is the slow path. You want the fast path to be your main choice. That's why you want to determine the root path cost, right? So the path information known as the internal root path cost is determined by the sum of all the individual port costs along the path from the switch in consideration to the root bridge, right? So when the switch receives the BPDU, right, it will add. Remember, it checks the BID, but it's also checked the ingress port cost of the segment to determine the internal root path cost, right? So how do we know this? Well, you can see that the default port costs are defined by the speed at which the port operates. By default, the cost we are talking about is the speed of the port. Remember, in switches, you have fast Ethernet and gigabit. So between gigabit and fast Ethernet, let's say you have these two choices. Which one will you choose? Of course, gigabit, right? It's lower cost in terms of path cost compared to fast Ethernet, because gigabit Ethernet is faster than fast Ethernet, right? So this is a table showing the default port cost suggested by IEEE, Institute of electrical and electronics engineering. They are responsible for a lot of the protocol use. If you recall, last time we studied, they are responsible for a lot of the protocols used within a local area network. In fact, a lot of those cable are specified by IEEE. Okay, so that is standardized, right? If you say, oh, Cat5, oh, what is Cat5? Well, the standard given by IEEE is Cat5 cable is okay, right? So the table here is, suggested by IEEE, right? So when Cisco manufacture the switch, by default, they follow the values defined by IEEE. And there's when you come up with a standard like this, IEEE always give version, just like your Wi-Fi version. There's version this, version this, version this, version this. Now it's, I think, 8.02.11 AX ka. What already standard. Always got version because they always improve, right? So the Cisco switch, they follow the IEEE standard 802.1D, and this standard is also known as short path cost for both STP and RSTP, right? So when your link speed on the port is 10 gigabits per second, the STP cost is 2. Remember, lower cost, better. And when the port is 1 gigabits per second, the cost path of that port is 4. 100 megabits per second, 19. 10 megabits per second, slow, right? Then they give higher, okay, 100. Okay, so we acknowledge RSTP, but we are looking at we focus on STP costs. So if your port is fast Ethernet, how you calculate? You have to add all the port costs, right? So fast Ethernet, one port is of course, when your port is running at, let's say, 100 megabits per second, the other port also compatible, right, at 100 megabits per second. You don't connect 100 megabits per second port and cable to 10 gigabits per second, right? If you do that, it always falls to the minimum. Okay, whichever port is the slowest, it will the speed of that path goes down to the lowest port cost. I mean, in the reality also like that now, right? So that means then your cost will be 19. Okay. Yeah. Now, even though this is given by IEEE and Cisco by default follow the IEEE standard, you can still configure yourself. Why? Because maybe you don't like the numbers given by IEEE. You want to have full control over your spanning tree. Which one is port? Which one is maybe for some reason you don't want the best the low cost path, right? Maybe you have 3 alternate. So you don't want the best path. You want the middle path rather than so. But ability to configure the port cost yourself, that means changing the values lah. Okay, changing the value of the cost per port depending on the link speed. Allow you flexibility lah to fashion your own STA network, right? Okay. Okay, you can see. Who knows whether it's good or bad? We don't know, but it depends on the admin, the network administrator. Give flexibility. If they want to follow this, good. But if they want to configure their own costs per link speed, then go ahead, right? Because they might want to choose for other reason a different path rather than automatically calculated low cost path. All right. So Does everybody agree with this? Determine the root path cost.
The cost number is what?
Yeah.
Is it just Mbps?
Yeah, this is the link speed of the port. And based on the link speed of the port on the, that goes to that you can reach the root bridge, then you give the cost. So if you have,
it's just a it's just a number only. The cost.
Yeah, this part, the Stp cost.
Yeah.
Yes, it's just a number, but this number is the one suggested by IEEE. So if you follow if you follow the IEEE standard, means it's more like for compatibility reason.
Okay.
Right. Yeah. So if you use this for one switch, then all switch you must use, or else, you might get undefined result. Right. By default, Cisco follow this. So if you agree with IEEE, then you agree with Cisco, then you just leave it be lah. Then the calculation of the path cost is based on these figures. Yeah. It's more like for compatibility lah. Right, easy for you as a system admin. I just accept the IEEE standard. All my switches by default have these values. During for the calculation of the next part, the root ports. Right. Remember, this algorithm runs automatically. The only way you can influence is by changing a few things. Like for the root bridge, how you influence is the priority. Okay. Now for the second part, the root ports, how you influence is changing the values, those port cost value. Right. But most of the time, for convenience, you just basically follow because it's IEEE and Cisco also support it. And by default, all the switches has got these figures for the root port election. Then, yeah, you might just. But sometimes, I can't think of a reason right now. But sometimes system admin want to bias the design of the spanning tree, right, path. So they still allow you to manually configure this, go in and change the port cost table. Right? The only thing is if you change for one switch, you change for all switch lah. Or else it's very difficult for you to figure out, how come the spot switch, consistency lah. Yeah. All right. So in fact, determining the root part cost is to do this actually. It's used to elect the root ports. Right? By determining determine the root path cost, then you can determine which port on the switch is root ports. Right? Now, I have to stop here because we already reached 3:37. Right? Before we go for a break, you guys have any question?
So far, no.
No.
No, okay. Only three of us. If you really have a question, just ask me. Because sometimes this is confusing also. First time to see. All right, so let me just stop my presentation. Stop my recording also. Okay. Right, so let us go for a break. Now is 3:38 minutes. It's 40, 45. Ooh. Yeah, it's okay. 10 minutes, 40, 45, 50. About 10:50 like that. Okay, no? 10:50, 3:50, sorry. 3:50.
Okay. Okay.
Okay, all right. So I'll meet you in the tutorial meet. I'm gonna log out this one, then we'll meet it using the tutorial meet URL.
Okay. Okay.
All right. Hello everyone. I noticed you restarted one. All right, so Right, so we only done until root bridge and non-root bridge, right? We haven't actually complete the root port, designated port, and non-designated port, and so on. Right, so just do the root bridge first. Okay. For all your questions, you just do the part of the question that mentioned root bridge or root port. No, root bridge. I think Pharaoh also is asked for root port. No? Excuse me.
So can only answer one thing only, not so since
Yeah.
only one of them is at the bridge and then the others.
Yeah. Exactly. Yeah. So once you finish, right? Maybe you guys can do revision lah. Revision. Is that okay? Because if I try to complete today, right? Then tomorrow we have less. That's what already content, right? So
Okay.
maybe we do revision lah, huh? Because now is week 3. Yeah. Recall that I asked for your timetable is because the CC is asking for it because she's trying to arrange suitable time, date and time, right? So that also simultaneous tests. Let me see. Cost file. Look at cost file, cost plan. So our test is going to be next week, week 4, right? E-test, midterm test. So since the test is on either channel and FHRP concept, same week, it's not going to be covering that. So I'm probably confident to say the coverage of the midterm test is week 1, 2, and 3 content, right?
Oh, does it include this tutorial?
Yes, include this tutorial. Okay, definitely tomorrow we'll be completing this tutorial. So basically, if you notice, the questions is the steps for the STP. Okay, example for Noel. Oh, Noel's doing straight away to designated. You can proceed to do, but I think without the lecture, that means you have to read yourself. But not necessarily to do. So Noel wants to try.
Oh, haven't covered. Oh.
Yeah, I don't mind. I don't mind you try. Noel. Right. So, but you can see the question is a root bridge, non-root bridge, root port. After that, you step by step. This is not step by step. You always try to look for root bridge first. Once you know the root bridge, the rest of the switch will be non-root bridge. And then root port. Once you know the root port, right? Root port on the non-root bridge, then you can find the designated, right? And then designated, then the alternate will be the non-designated port, right? And once you find out, the final will be the port that will be in blocking state. The blocking is the one that's going to stop the loop, right? But you have to go through all the steps here to achieve. Let me just show you that. Yeah. So basically the steps here are the steps for the STP operation, right? And the STP questions usually in this method, in this way. You can see the second question also the same. Root bridge, root port, designated port, non-designated. And then blocking port. Right? And then here also Farah. Unfortunately, Farah, you're asked to do root port, so that will have to wait until we cover, right? So
Okay.
yeah, same also after root bridge, then you find root port, and then explain the derivation. How you get the root port? Then you explain here.
Cannot just write that down answer and then no explain.
Answer, no answer.
You just write the answer and then you explain.
Oh, here, without explanation here.
Yeah, because you just asked for the which port and then that one. That one. Okay.
Yeah, here I'm talking about this. Yeah, I think you can see.
Only if it asks us to explain, then we can
Yes,
explain.
yes. It depends on the question. Yeah. Okay, just follow the question. So here for Farah, question is, once he figure out which one is the root port, then for switch W, then here Farah will explain how he get the answer, right? How he get the this answer, which is which is the port is the root port for switch W. What is the step to get that, right? So although it looks like just explain, but actually that means you have to still do this one, root bridge, and then finding out the root port, right? Then you can explain here. Question number 4. Again, same, illustrate which switch will be elected the root bridge, which will be placed in the blocking mode. Blocking mode is the last part of the step. Root bridge is the first part of the step, right? So by just asking this and this, you have to fill up the blanks, right? You see, once you say, okay, root bridge is selected like this, and then you say the root port is this, the selected port is this, the alternate port or non-designated port is this, then block these ports, isn't it? You can't know which one will be port will be in blocking mode unless you go through the steps, right? So Kelvin, for number 5, what are the 5 port states? We haven't covered that as well, and so as 6. Okay, the last step of the Stp operation. Okay, so you guys can what I suggest to do the revision is, let me just open up this. Where did I open this? Yeah, yeah. Let me just stop presenting here. Okay, so you can see, I think you can see, right? So I already opened the questions for this one STP not yet, but the previous one, previous the VLANs and inter VLAN already open, right? So you can check out the notes here, right? And you can see there's plum packet tracer if you want to try out to understand the operation, like for VLAN, inter VLAN, and then spanning tree, right? So I suggest if you do your revision, you can do this. And not only that, where's the one that I opened? Yeah, this one. Yeah. A little bit slow. How come? Mm. Mm. Yeah, so what I wanted to share is this, right? Oh, okay. So this one is yeah, right. This is my view, but once you see, oh, not this one, huh? Hang on, huh? Yeah, this one. All right. So they might ask you to open. Skip this one. Packet tracer, because some of the question require to view something in the packet tracer. So I do uh, encourage you to for your revision for preparing for next week. I will open the STP as well for you. Okay, so you can practice that one also. So uh, these questions that you'll be asked will be multiple choice lah in packet tracer, right? Sorry, in the NetHackett. But the questions that you're going to answer for the test is not MCQ, yeah. But even though it's MCQ inside NetHackett, it still helps you um, to test yourself lah. Which concept you already understood, which is not. So it by doing it, you know from the percentage you get, you can try many times lah. I think I allow about up to 10 times, right? You can try many times to basically to improve your what lah. If you try second time, maybe your marks will improve. For me, it's very useful for revision because from, for example, here, which command display information about auto MDX setting for specific interface, right? So if you want to see whether auto MDX is supported, which one, right? So it might not directly uh, help you with the kind of question that comes out, but it helps you to recall back, okay, what you've learned, and then some of the question not as hardware specific like this lah. Okay, it will be based on the theory, right? Right. Okay, but this is my view lah as the instructor. You guys will have questions, and then you can select and then proceed to the next one. I think towards the end uh, you'll be given the how many correct, how many percent correct, how many percent you got wrong, right? And which topic you got the most correct, which topics you get more errors lah. Okay, so that will should guide you to to read up on those topics that you still not confident about lah, right? Okay, so I leave you guys to do revision for the test next week. Okay, we'll be here. I will be monitoring. So if you have any questions you encounter, okay, whether you are reading through the online notes, or doing maybe you want to do the chapter exam. Okay, you're not sure about something, let me know. Right, guys?
Okay.
Okay.
The question 2,
Sorry, which one?
the question 2, the root bridge should be switch A, right? The location very weird. There.
This one. Talking about this
On,
question two.
yeah,
Right. So root bridge. So root bridge, let's see. Switch A, B is this one, C and D, right? B, this is B, this is A, this is D, this is C. So remember, how do we elect? We look at the priority first. So we notice all the priority are the same, correct?
yeah,
Yeah. So MAC address
yeah.
0,
switch-
00 D0, 001, 002, 00E0. So which one become root? Which one is the lowest?
Yeah, the switch A should be
Switch
lowest.
A. This become the root bridge.
Yeah, so the root port thing, so I don't understand because the location is very weird. I don't know how to check for
Yeah,
the root port.
root port. Yeah, that's why I said root port.
Yeah.
I was about halfway explain in my explanation about the root port. The root port we just learned, okay, about the path costs, right? So in order to get the root port, the next part of our explanation is we elect the root ports. To elect the root ports, we need to find out the root path costs. The path costs, remember, we have to look at the ports that allow us to get to the root bridge. So if the root bridge is switch A do not have root port anymore, right? Because it is already the root bridge. So we are looking at switch B, switch D, and switch C. Okay, and then we are going to look at the port itself, the path, the cost of the path. Remember that from our table, gigabits, the cost is 2, the lowest cost for that, because it's 10 gigabits, very quite fast. 1 gigabits per second is cost is 4, 100 megabits per second is 19, 10 megabits per second 100. So on our switch, typically we have 1 gigabits per second and 100 megabits per second. So it's between 4 and 19. So if you imagine yourself being switch B, okay, the cost is gigabit, right? Gigabit, because it's G01. Can you see that?
Oh,
One, right? Okay, so that port, what is that port? That port is G01. So G01, based on our table, is the cost is 4. So this port G01 is 4. Okay. Now F04 does not lead to root bridge. So F04, none, leave it first. Okay. So the other path is F021 or F022. Okay. Let's say we take first F021. So fast internet, 100 megabits per second is 19. So this path between switch B to switch D is 19. Okay, from switch D to go to switch A is also 19. So 19 plus 19.
38. Oh, like that. Oh, okay, understand.
Yes, yes. So the second one, F02. So B to switch C is also fast internet, 19. C to D is gigabit. Gigabit is 4. 4 plus 19. Really. But again here, another 19. So it's 19 plus 4 plus 19 in order to get from B to C to D to A. So which one will be the root port?
Oh, the G01 on the switch
Yeah.
B.
Yes.
Oh,
Okay. So basically that's the topic next topic that we cover tomorrow lah. But I tell you guys first lah. Huh? So maybe you get a repeat tomorrow. Okay. All right.